Right. So we're moving into 3D graphing. So getting a sense for what functions look like in 3D. I want to start off by taking you through a little bit of a tour of two applications you can find online. They're listed on our Quarkus extra resources. So I just put up GeoGebra 3D and CalcPlot 3D. So if you get nothing else from today's lecture, go to those websites. If you go to those websites, you can spend a half hour and learn more than I'll teach you in 6 hours. You'll learn more playing with these tools than I can possibly teach you by saying stuff. Yeah, so let's have a look at them. So GeoGebra 3D looks like this. So it's very much like Desmos or whatever, but it can plot things in 3D, which is super duper duper helpful. So in general, drawing graphs is really hard. Okay, it took people 20,000 years to figure it out. So it's very hard. So I recommend that you play with GeoGebra a little bit to graph some things. So like here's the graph of a parabola. When you look at it in 3D, you get this cool sheet thing. Right? So our height coordinate is z. We're saying z is x squared. And when we graph this, we get this kind of U-shaped thing. What does that tell us about the x-axis? Which one is the x-axis in this picture?
Red.
It's the red one. Yeah, does it look red? Yeah, it looks pretty red. Yeah, so that tells us that this guy is the x-axis. Right, and if we switch this to y squared, then we get the green axis is the y-axis. With this, we can make really beautiful kind of spinny visuals. Ooh, so nice. Okay, but we can put in more complicated functions. So probably my second favorite example in this whole course is this function. Okay. This function, if you play with it, look at its graph, really think about it, you'll learn all sorts of things in multivariable calculus. Okay. Very, very, very nice, special function. Okay. Perfectly symmetrical, it's very round. Okay. Lovely, lovely, lovely example of a function. This is about as complicated a picture as we'll ever ask you to draw by hand. Okay. So you might want to copy this example down before we go on. Take a moment, try and copy that sketch, label it z is x squared plus y squared. See some people taking a photo, good idea. Excellent. If you look at it from above, it looks like a circle. Also from below, it looks like a circle. Hello. But as soon as we change from this really, really, really simple example, drawing things becomes very hard. Okay, so my favorite example in this class is this. So it's x squared minus y squared. Okay, beautiful, beautiful function. But as you can see, very unwieldy to draw. Okay, so when we look along the y-axis, right, we see a parabola, we see a parabola in one direction. When we look along the other axis, we see a parabola in the other direction. So it's kind of a parabola upwards in one direction and a parabola downwards in the other direction. Okay? A nice model for this surface you carry with you all the time. So if you look at this part of your hand, right between your thumb and the rest of your hand, it's a parabola upwards like this. Yeah, I see some people looking at their hand, that's great. So you look at it as a parabola upwards like this, and a parabola downwards in the other direction. Okay. So kind of a neat thing about this surface is that it has what's called negative curvature, and that's what allows it to be flexible, why your thumb's flexible. In this direction, we've got upward parabola. In this direction, we've got downward parabola. Okay, so very, very, very helpful example. But yeah, so you can do all sorts of crazy things in GeoGebra. Do like sine squared. Ooh, that's cosmic. Or maybe we could like multiply it. Oh gosh, what have I done? Oh no. Right. As you can see, graphing things is very hard. Okay, so there's GeoGebra. There's another graphing application that I want to show you. So this one is also on Quirkus, and it's listed as CalcPlot 3D. So CalcPlot 3D is here. And this is like by math professors for math professors. So it's a little, the interface leaves something to be desired, but it can do really cool things that GeoGebra can't do. So first off, it produces these nice pictures, but it's got a lot of different kinds of functions. Okay, so you can graph many different kinds of things. It also has a lot of examples, and these examples are neat to look at. So you want to see an example of a curve. All right, there's a curve. Isn't that ridiculous? So this is a parametric curve that someone wrote down the equation for. So it can plot parametric curves in 3D. It has a cool knot, apparently. There's another cool knot. Ooh. Okay, so there's space curves, implicit surfaces. There's an ellipsoid. Awesome. So yeah, lots and lots and lots of examples. Yes? Yes, it is. I bet you they've done that. Let's see. Mobius ring. There's a round cube, whatever that means. Round cube. Whoa. Let's see, it's probably a parametric surface. No, it doesn't look good. There's a Klein bottle. There's a Klein bottle, which is pretty cool. So that's two Mobius bands stuck together. Or a very good design for a vacuum. Or some kind of sea monster. Okay, sorry, I'm very distracted. I wanted to show you. Sorry, I love my job. This is just so much fun. So yeah, play around with this thing. It can do tons of stuff. There's one more feature I want to show you, and then I will stop playing with the computer, and we'll get on with the math. Okay, so let's just completely go all the way back to this guy. Okay, so one of the things that CalcPlot 3D can do that GeoGebra cannot do is level curves. So if you've got a surface like this, you can click this kind of red icon here. And what that will do is it will generate what's called a contour plot. Okay, what that is you take this surface and you cut it by different heights. So you cut it height 1, height 0.9, height 0.8, height 0.7. You cut it different heights, and you get the following thing. Ooh. Right, so this is what happens when you take your surface and cut along parallel planes. You get these sort of rings that decompose your surface. Okay, so this is the major thing that GeoGebra can do very easily. That we'll investigate a little bit more what those are. But very, 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 very helpful tool for visualizing what's going on. Yes. Okay. Thoughts there? Questions there about these things? Yes.
So this is like those maps with the altitudes that hikers use?
This is exactly like one of those maps that hikers use. Yes. Yes.
I don't know what those things are called. Yeah.
So these are called topographic maps. So let's look at some of those guys.
Yes.
So this shows some asparagus. It was a risky click. Like, we could have got some porn ads or something. I just kind of jumped into that. Then I was like, oh no, what have I done? Anyway, sorry. This shows a decomposition of mountains into equal heights, right? So the mountains are going up. You go to the top of the mountain, you get to Mount Macy. Right, so these are exactly like topographic maps. Another thing. Right, where we decompose a mountain range into a bunch of curves that are all the same height, and that gives us a picture of the region in 2D. Yeah, yes, it's exactly that. Other thoughts there, other comments? Okay, so we'll head into the details of this stuff. I encourage you to go and look at GeoGebra and kind of plot. Okay. All right, so what are we up to today? We're going to look at functions of several variables, and then in the next lecture we'll do continuity and partial derivatives. Okay, so let's turn this guy off. Okay. Okay, so at the end of last lecture, we had this point about planes and normals. Okay, so we were saying normals, and we were saying that we could write a plane in the following form. Where we have xyz dot some constant, or dot our normal gives us some constant. Okay, and the question came up, and I thought it was just like a totally awesome question, is when this is not 0, is the thing no longer, is the normal no longer orthogonal to the plane? Okay, really, really, really good question. I had to kind of think about it a little bit. I want to say how it works out, and then we'll transition into functions of several variables. So, question. It turns out the answer is quite subtle. So what happens if this constant is not 0? We get a situation like the following. So we get some line, and we have a normal vector. Okay, so here's our plane, and there's our normal vector. Now, there are two senses of orthogonal that we can use here. Okay, so the first is we can ask, is the vector from the origin to a point orthogonal to n? Right, so we go from the origin to a point on the plane and say, is that orthogonal to n? And what's the answer in this picture? Okay, I got like a couple no's, but could I get a big like, no? No, it's not orthogonal. No, right? This needs to be 90 degrees, and it's not. However, this guy is 90 degrees. So the plane to the normal, the plane itself as an object is normal, but the vectors on the plane are not. Okay, so vectors, so let's say a vector to the plane so a vector like this vector v, from here to here, is not orthogonal. Okay, so we pick a point, we go there, it is not orthogonal to n. However, if we have a vector in the plane, then it is orthogonal.